This is an extension problem from a problem in Giancoli's 7th edition Physics Principles with Applications. I was working with a student on chapter 3, number 49, and he wanted some more options for it, some more varieties. So here's the basic problem. We've got a lifeguard who we know can swim, oh, it's not given here, but the lifeguard can swim at 2 meters per second. We've got a river going 1 meter per second. And the first problems in the book don't give us the second lifeguard up here. I said, well, what if there's a lifeguard up here 50 meters away who says, hey, I can try to catch up with that person, or I can have this person here swim to catch them. So the question is, what angle should the lifeguard swim at in order to be able to catch the kid? So go ahead and try to solve that one. Pause the video, come back, we'll see how you did. Okay, so first judgment, you probably said, hey, the shore's not moving, so the river must be the thing that's moving. So let's look at what that looks like. And we've got a situation, the river, the kid, the lifeguard is going down the river, and what do we notice? Both these characters are moving. So you gotta do X and Y for both of them. Kind of complicated. What if we shift our frame of reference and instead we say, let's say the shore is moving and the river is the same. So we have something that looks like that. And in this case, notice compared to each other, only the lifeguard is going to be the one that's moving. And this is similar to all objects in physics. We don't care about the fact that in most cases that we're going 800 miles an hour in the US. We're all moving 800 miles an hour on the surface of the Earth. So we just ignore that. We say the frame of reference is our rotating Earth. So go ahead with this. If you had trouble, see if you can solve it this way and come back and we will go through, I will show you how to do it. So take a break, see if you can do it. Okay, you're back. So now we're looking at the lifeguard. Let's look at our x-axis first. We know the velocity is going to be 2 cosine theta, because if that's our angle, cosine is opposite over adjacent. And we know delta x in the x direction is 45. So we're going to rearrange this to solve for t. Why did I choose t? Because I know I've got t in each equation. And so I'm just going to rearrange this, or my velocity equation, t is equal to delta x over v. And then I'm going to plug in my values, and I've got, oh, what? Time is our 45 meters divided by 2 meters per second cosine theta. So there's a final equation there. We got 2 unknowns though, right? So we know, let's go over to the y-axis. So in the y-axis, my velocity is 2 meters per second times the sine of theta, because it's opposite, right? So then we're going to say, how far do we need to swim? 50 meters. Remember, we're saying the kid's not moving. The kid in the river, the kid's just bobbing down the river. So we're looking to solve for theta. In the end, that's our question. So let's leave velocity on one side of our equation. Here we set time on one side. Let's leave velocity all by itself. So velocity is delta y over t. We plug in our values. We get 2 sine theta is 50 over t. Now you've got 2 equations, 2 unknowns. Should be able to solve for it. Go ahead, try your algebra, see if you can get that, work through that. That should be pretty straightforward. Take a break and come back, and I'll work through the rest of it with you. Give you a hint, the answer is 48 degrees. Okay, so here you're back. So we're going to plug in this t value here from x over here, and we get, oh, 2 sine theta is equal to 50 over 45, 2 cosine theta. We can rearrange that. We can flip this, put the 2 cosine theta on top. A little bit more algebra, rearrange, get all of our thetas on one side, cancel out the 2, sine over cosine we remember is tangent, and then we're going to do the inverse tangent of that number to get our angle, and it is 48 degrees. Hopefully that helped you with this. Enjoy, and stop back for more videos. Bye-bye.